Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the process of statistical inference by comparing proportional reduction in error between two models. Let's revisit the general data analysis framework as a refresher. When we conduct data analysis, we are trying to create a representation of the data. We can use the basic equation, data equals model plus error, to conduct many different types of statistical analyses. Data are the actual scores or observations. Model is the representation of the data that's used to make a prediction about each score. And error is the part of the data that the model fails to represent. So far, we've been working with the simplest model. The very simplest model we can specify would be to have a single parameter estimate B0. B0 is some constant calculated from our data, and then we have individual error values for each person. In the models that we've discussed so far, B0 is a measure of central tendency, such as the mean, the median, or the mode. Recall that we are both trying to include predictors that improve the model and to not include too many predictors so that we can keep the model relatively simple. To do this, we compare competing models by calculating the proportional reduction in error. The proportional reduction in error involves comparing two models to determine whether adding additional predictors is worth our while. The compact model will usually represent the null hypothesis. This is the model hypothesizing no effect or a simpler effect. The augmented model will represent the alternative hypothesis and include the additional predicted effects. We can define a proportional reduction in error as the amount that error is reduced by adding parameters. Another way to think about this is that proportional reduction in error is the amount that error is reduced in the data when we examine the alternative hypothesis. If the leftover error in model A is similar to the error in model C, the ratio of the two will be close to 1, and proportional reduction in error will be close to 0. This would indicate to us that the additional parameters in model A, the augmented model, are probably not worth it, and we should stick with model C, the null hypothesis model. If the leftover error in the augmented model is much smaller than the error in the compact model after adding the additional parameters, the ratio of the two will be close to 0 and pre will be close to 1. This indicates to us that it's probably worth it to add the additional parameters to our model and that we should go with model A, the augmented model, or the alternative hypothesis model. Very generally, this is how proportional reduction in error gives us similar information to hypothesis testing. But now let's talk about how to concretely calculate pre and actually use pre in null hypothesis significance testing. Here's how we actually calculate pre. We first start by calculating the error for each model. Remember when we talked about types of error, the sum of squared errors has the mean as its best estimator. That is, the mean minimizes the sum of squared errors. The proof for this is in your textbook. If we consider the mean to be the parameter B0 in the simplest model, then we should use the sum of squared errors to calculate error. So the first step toward calculating pre is to calculate the sum of squared errors for the compact model or the null hypothesis model. And the second step is to calculate the sum of squared errors for the augmented model or the alternative hypothesis model. We then use these sums of squared errors to calculate the sum of squares reduced. This is the amount of error that is reduced by using model A or the alternative hypothesis model instead of model C, the null hypothesis model. The sum of squares reduced is simply the difference between the sum of squared errors for model C and for model A. Once we have calculated the sum of squares reduced, we can formally calculate pre, which is the sum of squares reduced divided by the sum of squared errors for model C. Conceptually, this is the proportion of model C's error that is eliminated by adding the additional predictors that we added to model A. Let's take a look at these formulas. The sum of squared errors for model C is calculated by subtracting the estimate of B0 for model C from the observed values from the data. The sum of squared errors for model A is, and squaring those values, and then summing. And then the sum of squared errors for model A is calculated in the same way, but this time we actually use the estimate of B0 for model A. So if we're thinking B0 is a mean, for example, there's a mean for model C and a mean for model A, and we plug those into the formulas for the sum of squared errors for each of the models. And then once we have those values, the sum of squared errors, remember each is a single value, we subtract the sum of squared errors from model A from the sum of squared errors for model C, and this gives us the sum of squares reduced. Then once we have the sum of squares reduced, and we already have the sum of squared errors for model C, we can calculate pre, because pre is just the sum of squares reduced divided by the sum of squared errors for model C. I've shown you the alternative formulas for proportional reduction in error as well. If this is confusing, we will go through example calculations of proportional reduction in error in class. So I have just described how to calculate proportional reduction in error, but we need a way to make some judgment about the size of proportional reduction in error to decide whether the additional parameters are worth it. Last week we learned about sampling distributions and using them to determine the likelihood of score occurrence, for example, for a mean. Well, much like the mean has a sampling distribution, proportional reduction in error also has a sampling distribution, and this is because proportional reduction in error is an estimate. So just like the sample mean is an estimate of the population mean, proportional reduction in error is an estimate of the true proportional reduction in error in the population. Remember that we can use null hypothesis significance testing steps to determine how likely it is we would observe a mean score given the null hypothesis is true. We can also use NHST to determine the likelihood of observing our calculated proportional reduction in error, given that model C is true. Remember that model C, the compact model, represents the null hypothesis. So we are determining the likelihood of observing our calculated proportional reduction in error, given the null hypothesis is true. If we determine that the calculated proportional reduction in error is unlikely, given the null hypothesis, then we reject the null hypothesis model, that would be model C, and we retain the augmented model, model A. That's the model with the additional predictors. Let's go through the steps of NHST for pre. The null hypothesis and alternative hypothesis are not that pre is equal to 0 or that pre is not equal to 0. Remember that we will already have estimates of B0 for models A and C. For example, these would be the computed mean estimates in the simple models that we've been discussing. I've given an example here that, for example, for model C, we might estimate a mean of 50. But for model A, we might estimate a mean of 42.7. In this situation, the null hypothesis would be that mean estimate for model C, and the alternative hypothesis would be that mean estimate for model A. Again, it's whatever parameter estimate we are testing that we're plugging in to calculate pre. The second step we know for NHST in general is to determine the rejection rule. Now, because pre has a sampling distribution just like the mean, we actually can calculate critical values for pre. And we can get those values using an F table, and also there's the table in your book. To do this, we need degrees of freedom, and each model will have a different degrees of freedom. So the degrees of freedom are the total number of scores minus the actual number of parameters for model A, the augmented model. That's our degrees of freedom to get the critical values for pre. And then our rejection rule is to reject the null hypothesis or reject model C if the observed pre is greater than or equal to the positive critical pre value. This is a one-tailed test because we are always looking to calculate a higher observed proportional reduction in error. The third step is to calculate the test statistic. And so in this step, we are calculating pre, but we are also calculating a statistic called F, the F statistic. And I'll talk more about F on the next slide. But we know to calculate pre that we subtract the sum of squared errors from model A from the sum of squared errors from model C, and then we divide that value by the sum of squared errors for model C, the null hypothesis model. Once we have our test statistics, we can make a decision about the significance of pre based on our rejection rule. Now let's talk about the F statistic. We actually conduct null hypothesis significance testing for pre and for F. We use proportional reduction in error, pre, when model A, the augmented model, only has one additional parameter. But we calculate F and we conduct NHST for F when model A has more than one additional parameter over model C. So if model A has two or more additional parameters compared to model C, then we need to calculate F and conduct NHST steps for F. So we actually do this based on values of pre, and we need pre to understand what F is. So if we want to calculate proportional reduction in error for models with more than one additional parameter, then what we're really interested in there is looking at the proportional reduction in error per parameter in that model. We want to know the exact contribution of each parameter in how it reduces error. So for example, one parameter might reduce error a lot more than another parameter, and we want to know what the individual contributions are. And so to get the actual value of pre per parameter in those models that would have more than one additional parameter, we calculate pre in the same way that we would calculate pre for a model with one parameter. But we divide pre by the difference between the number of parameters in model A and the number of parameters in model C. This is how we get the pre per parameter. And this, you can see in the second to last bullet, is the numerator of the F statistic. Then we also want to get the remaining proportion of error for models with more than one additional parameter. And to do this, we already, in the numerator, we calculate 1 minus pre, which would be the remaining proportion of error in models with only one parameter, the same way that we would calculate it. But then we divide that value by the number of scores minus the number of parameters in model A, recalling that in this situation, model A has more than one additional parameter compared to model C. And then we can see that this is the denominator for the F statistic. So pre per parameter for models with more than one additional parameter is the numerator for F, and the remaining proportion of error for models with more than one additional parameter is the denominator for F. F also has a sampling distribution, and so we can conduct null hypothesis significance testing for F and find the likelihood of observing our F value given that model C is true, the compact model or the null hypothesis model. We can also consider the types of decisions we would make from null hypothesis significance testing in this framework. By now, it should be clear that model C is analogous to the null hypothesis. Our compact model is the null hypothesis. So when we're thinking about this in terms of model C, type 1 error would be a situation where model C is true in reality, but we reject model C in favor of model A. This is where we would retain model A, the model with additional parameters, and consider it better than model C, even if model C is the true model. A type 2 error would be when model A is actually better than model C in reality, but we retain model C, the model with less parameters. And then power would be when in reality model A is better than model C, and we retain model A. We determine that model A is better than model C.